differentials. And our basic idea with, at the beginning of this chapter anyways, is to kind of extend what we've done, what we know about differentiation to multivariable functions. So we've talked about how we take a partial derivative. Yesterday we talked about higher order partial derivatives. And this is just another thing that in Calc 1 you did with derivatives. So we're gonna touch on it today, just kind of extend the idea. So for a single variable function, and this was from back in Calc 1, after you learned how to do derivatives, we came up with what we called the differential of y. We called it dy, and dy was f prime of x dx. And the way you used it, the way we use it here is this is the linear. We're using the tangent line to approximate the function. So this differential approximates how the function changes by using the tangent line rather than the function itself. So this is a linear approximation of the change in y. We're using the tangent line. And we're going to do the same thing with a multivariable function. So if z is some function of x and y, we're going to call delta x and delta y increments of x and y. And that just means we have a small change in x and a small change in y. And the increment of the function is just delta z. We're going to call it delta z. And that's how the function changes when we move these small distances delta x and delta y. So that's going to be f of x plus delta x, comma y plus delta y, minus f of xy. So this is just how much our function changes as we change the variable x and y by these increments delta x and delta y. And we'll draw a little picture to show what we're talking about here. So we're just changing x and y, and we want to figure out how our function changes when we change x and y. So you guys good with this? Okay. So let's draw a picture to show what we mean geometrically. So here are our axes. And our surface is up here somewhere. So there's our surface. And I'm going to do the x's. We'll do the x's in red. So we're going to call this is x. And then we're going to go out here a certain distance. And from here to here is delta x. And we're going to do the same thing on the y-axis. So over here we're going to say that this is y, and then we're going to go out here to this new position, and this distance is delta y. And I'm going to project these out this way along my xy plane. Do those a little better here. And we'll do the x's as well. So we want to know how our function changes as we go from this point for x and y to this point. So let's project those up onto our surface. So we're going to go straight up here, and we'll go up here. And on our surface, we're going to move from this point at xy to this point at x plus delta x and y plus delta y. And we'll project those over onto our z-axis. And this little distance between these two is delta z. So that's what our increments are telling us. We're moving from this x-coordinate over to here. This distance delta x, we're moving from this y-coordinate over here to a distance delta y. And we want to figure out how much the function changes as we move that distance. Does that make sense? So we're going to define the differential of our function, our two-variable function, we're going to find the differential, we call the differential dz of our function as a change in height of the tangent plane from this point to this point. So we're going to find our tangent plane at this point on our surface, and we're going to find the tangent plane at the point at our new point, and we're going to approximate the change in the function by how much the tangent plane changes. So like we did with the single variable function, we're saying that rather than looking at this complicated surface, let's just look at a plane, and we're going to put a plane on our surface at this point and figure out how high that plane is. And then we're going to put a plane on the surface at this point and figure out where that plane meets the z-axis and figure out the change in height of the plane rather than the change in height of the function. Like we did in single variable calculus, we looked at the tangent line and we saw how the tangent line changed from one point to the other, and we approximated the change in the function by that change in the y value of the tangent line. Same idea. So we're going to find the differential dz as a change in height of the tangent plane. And we're going to figure out how it changes from the point xy to x plus delta x and y plus delta y. And we can show, we're not going to, it takes a little work, and it's a little complicated, having to do with calculating tangent planes and that kind of thing. We know how to do it, but it's more complicated than we want to do right now. We can show that dz are differential our change in height of the tangent plane is dz dx delta x plus dz dy delta y. And we usually just write dz, everything in terms of d's. So this is, we usually write dz dx dx plus dz dy dy. And just so we're clear, we're not saying that we're not using this dx and this dy and this dz as a infinitesimal. We're not saying that they're super tiny. This is just a shorthand notation for a small change in z, a small change in x, and a small change in y. So we're not using these dx's and dy's like we do when we write a derivative. So we're just using a shorthand to show that it's a small change in x and a small change in y. And this, what we call this expression, this is the total differential of our function. So when you see that phrase total differential, it's referring to this. And again, I just want to emphasize that at a particular point, dz, our differential, our total differential, is a linear function of x and y. We're using a linear approximation to our increment, to our small change at a particular point. And as delta x and delta y get smaller, as our increments of x and y get smaller, dz is a better and better approximation to delta z. And eventually, delta z, the small change, as delta x and delta y get smaller and smaller, delta z and dz turn out to be the same thing in the limit. So just like we did in single variable calculus, we're just using a linear approximation. As our little change in our variable gets smaller and smaller, our linear approximation becomes a better and better approximation to our function. So the way we use differentials and the kinds of problems that we're going to work on have mainly to do with approximating functions. That's really the kind of the emphasis that we're going to put on is doing approximations. And you did the same thing back in Calculus 1. You kind of approximated a function with your tangent line. And that's what we're going to do with these. So we'll do a couple of examples of how we're going to use these, and then I want to talk just really briefly about another use, another way that we use differentials, not what we're going to do, but how they're used in multivariable calculus. So we want to evaluate f of 1, 2 and f of 1.05 2.1, and then we want to find delta z, so the change in the function between these 2 points, and then we're going to approximate delta z using our total differential for our function equals x e to the y. So we're going to compare our approximation to actually computing our function. So first off, we're going to calculate our function at the 2 points. So f of 1, 2 is just 1 times e squared. And if I plug that into my calculator, that's about 7.389. And if I calculate my next point, 1.05, 2.1, so I get 1.05 e to the 2.1, and that's approximately 8.574. And now we're going to, and our delta z, our change in the function between those 2 points, if I subtract those, I get it's about 1.185. So change from here to here is about 1.185. Now we're going to approximate this with the total differential. We're going to do dz equals dz dx delta x plus dz dy delta y. So dz dx equals what? E to the y. And dz dy x e to the y, right? And delta x from here to here, 0.05. And delta y is 0.1. So our total differential is just 0.05 e to the y plus 0.1 x e to the y. So at 1, 2, the point we're interested in, dz is just e squared times 0.05 plus x, we're starting at, our point is 1, so we just get plus e squared times 0.1. And we get approximately 0.3695. $7.389, and we get approximately our total differential tells us that this is approximately 1.1084. So that's our approximation for the change in the function. And the way this comes in, the way that we would use total differentials, we'll talk about it in just a minute. Use them a lot for error estimates. So if you make an error, or if you're making measurements and your delta x and delta y is your error in your measurement, this can tell you something about the total error in your measurement if what you're measuring depends on 2 variables, and we'll do an example of that. Or you might use this for like in a computer programming application where you have a really complicated function, and it's easier to evaluate your differential, your approximation, than the function itself. because you see here, you see we're doing e to integer exponents. Where to evaluate our function, we had to do decimal exponents. Integer exponents are a little easier for computers to deal with than decimal exponents. So those are a couple of ways that you might use this. All right, let's look at another example. Questions before we go on? All right. We want to find, in this example, we want to find our function. And use the differential to approximate the quantity. And our quantity is 2.03 squared times 1 plus 8.9 to the third minus 2 squared times 1 plus 9 to the third. And now to approximate this, now our change in our function, remember delta z, our increment is f of x plus delta x, y plus delta y. So we're looking at the form of this, minus f of x, y. So looking at the form of this quantity and looking at the form of our increment, we're comparing the forms. What is our function? What is our function going to be? F of some xy, I'm just going to say xy, equals, any ideas? Compare this expression to this expression. So at this particular xy, we have something squared times 1 plus something cubed. So I'm just going to write this as at this particular point, at this particular xy, f of xy equals 2 squared times 1 plus 9 cubed. That's going to be our function at this point. So let's let f of xy equal x squared times 1 plus y to the third power. And our x0, y0, our initial point from this is 2, 9. Just comparing what we have here to this, we decided this is going to be our function at some point. So this is our point based on our choice. And delta x, if we choose this way, delta x is going to be what? From 2.03, 0.03. So we're going from 2 to 2.03. And delta y, we're going from 9 to 8.9, negative 0.1. So there we have we found our function, x squared times 1 plus y cubed. We found our delta x and delta y. This is our point that we start at. Now we can find our differential to approximate this quantity. This quantity wouldn't be hard to calculate. You can plug this into your calculator, but we want to approximate it using our differential since we have this fancy new tool to work with. So df dx. This is our function. What is df dx? 2x. 2x times 1 plus y cubed. And df dy. X squared times 1 plus y squared. So now we're going to calculate our differential. So we're starting at our 0.29. df is going to be plugging in our numbers. 4 times 10 to the third times 0.03. This is df dx at 2.9 times delta x plus 3 times 2 squared times 10 squared times our delta y, negative 0.1. And if I calculate this out, turns out that this equals 0.
Where are you getting the tens?
1 plus y.
Oh.
Y is 9. So 1 plus 9, that gives me my 10. So this is a little easier. For this particular function, it's not a huge difference, but this is a little easier to calculate than this. A little bit. If you had a really complicated function, something like this might be quite a bit easier to calculate than something really complicated like this. So that's how we're going to, that's how we use it as why we might want to use it as an approximation. All right, let's look at one error analysis problem, and then we're done. Questions? Okay. So in this example, we have a right circular cone. Our radius and our height are measured with possible errors of 4% and 2%. We want to approximate the possible error in the volume. So whatever ruler we use to measure the radius and the height of our cone, we get this much accuracy, and we want to figure out how much our calculation of the volume could be wrong. So we want to look at dV, our differential for the volume. So dV is going to be dV dr times dr plus dV dH dH. Our volume is a function of radius and height. And for a right circular cylinder, our volume, do we remember how we find the volume of a right circular cylinder? area of the base times the height. So 2 pi r squared h. And also remember that when we have our error as a percentage, this is percentage is a relative error. So relative, yeah, you do this in physics? Relative error, so dr, the change in r over the actual value, that's what this tells us, is 0.04. These are relative errors. And dh, the change in h over the actual height, is 0.02. That's what the 4% and the 2% tell us. These are relative errors. So if I calculate the total differential of dv, we're going to calculate using this as our function and write this expression with this as our function. So dv equals, dv dr is going to be what? 4 pi r h, and we're going to multiply by dr, plus dv dh, 2 pi r squared, and then we're going to multiply that by dh. And we want the error, we want to approximate the possible error in the volume. So we want dv over v. That's our relative error in the volume. So we're going to divide this expression by our volume to get dv over v. So we get 4 pi r h and dr over let's see, what did I do here? My volume isn't 2 pi r squared h. My volume is just pi r squared h. So this should be a area of the base is just pi r squared. It's just a circle times h. So I was off by a factor. I was thinking of surface area. So we're off by a factor of 2 here. So this should be 2, and this should be just pi r squared dh. So we have pi r h dr divided by our volume, pi r squared h, plus,
Wait, what is the top be 2 pi r?
yes, 2 pi r. Thank you. Plus pi r squared dh over pi r squared h. And when we write this out, we cancel. We get 2 dr over r plus dh over h. And we know what dr over r and dh over h is. So this is just 2 times 0.04 plus 0.02, which gives me 0.10, which is 10%. So our possible error, our relative error in the volume would be 10% if we measured the radius and the height with errors of 4% and 2%. So that would be an example of an error calculation. Questions? Okay. Homework. Oh, there's one thing that I wanted to talk about before we do the homework, this is just a really short thing. We use the idea of increments to define differentiability of multivariable functions. And the reason we do that is with a multivariable function, we can have the derivative exist at a point where the function isn't continuous. For a single variable function, if a function isn't continuous, then the derivative doesn't exist at that point. For a multivariable function, the derivative can exist where the function isn't continuous. For a single variable function, we say that the existence of the derivative defines differentiability. If the derivative exists, our function is differentiable. Not the case for multivariable functions. If we're working with nice functions, if our first partials are continuous, then our function is continuous. But we can have functions that are differentiable but not continuous for multivariable functions. If you're interested at all, on pages 917 through 920 talks about information about differentiability and gives some examples of functions that don't behave nicely. But we use a differential, the total differential, to help us define differentiability of a multivariable function. It turns out if our function behaves nicely, the total differential gives us a nice way to define differentiability. All right, now homework. Page 921. There you go.